Swayam Prabha. Digital India. Educated India.
So, this class I will discuss that how we can determine the group load carrying capacity of the pile, and then how we can determine the settlement of a pile group in clay. So, this is the problem which is given here, that design a pile group consisting of RCC solid piles for a column of size 650 millimeter cross 650 millimeter, carrying a load of 1125 kilonewton, and then the soil data that is given, it is a clay extending to a greater depth, and the other data are data of the soil deposit are the CC value is 0.1 initial. I should write these values. So, CC value is 0.1, then initial void ratio E0 is 0.9, saturated unit weight of the soil is 20 kilonewton per meter cube, then unconfined compressive strength, that means QU is 70 kilonewton per meter square. Okay. So, the Cu value will be Qu divided by 2 100 cohesion, and that is 70 divided by 2, that will be 35 kilonewton per meter square. Then permissible settlement SA is 25 millimeter for the pile group, and design the pile group by considering both bearing as well as the settlement criteria. The water table is at the ground surface, factor of safety is 2.5, alpha value is taken as 0.7, and depth correction factor is correction factor for the effect of 3D consolidation or pore water pressure is 0.7. Okay. That means pore water pressure correction is given. So, now we have to calculate we have to design the pile group. Okay. So, this is not the pile size, this is the size of the column. For this particular column, we are designing the pile group. So, load is coming is 1125 kilonewton, the total load. So, now for the pile group, first we will calculate the bearing capacity. Okay. So, bearing capacity, first we will consider the single pile consideration or single pile failure. So, for single pile failure QUS, that will be CUNCAB plus alpha CUAS, that we know that the equation is given. First one is the tip resistance, second one is the friction resistance for the clay, and Cu is given 35, Nc is equal to 9, and area is pi d square, d is diameter is so first we are assuming the first trial, the diameter is 0.3 meter. So, diameter of the pile is 0.31. So, this is for the first trial, it is assumed. Okay. So, first trial it is assumed 0.3 millimeter. So, that is pi d square by 4, then alpha is 0.7, Cu is 35, into pi dl, pi d is 0.3, L is taken as 15 meter. So, for the first trial L is taken as a 15 meter. So, here also L is not given. So, what are the things you have to determine? You have to determine the diameter of the pile, length of the pile and spacing between the piles. So, diameter and length we are assuming for the first trial, and length is assumed as a 15 meter. Okay. So, that means here this value is 354.6 kilonewton, and we have assumed again another assumption that 9 pile in square group. That is also assumption for the first trial. So, that means the number of pile also you have to assume for the first trial. Then we will check whether that assumption is correct or not. If it is not correct, then you have to redesign this. Okay. So, that means the 9 piles we are assume are in square pattern. So, the group load carrying capacity based on the single pile failure will be 9 into 354 into 6. So, that is 3191.4 kilonewton. So, that is for the single pile failure consideration, and then we have the 9 piles in square group. So, this is the 9 piles and it is distance is 0.3. Again we are assuming for the first trial the spacing between the piles is 1 meter. Okay. Here also, because as per I square it is minimum spacing is 3D. So, we are taking 1 meter. So, the spacing between the pile, that is also 1 meter, and that is also we are assuming for the first trial. So, the B value will be 2 into S plus D. So, 2 into 1 plus 0.3, diameter of the pile is 0.3. So, this will be 2.3 millimeter, meter, because this is 1 meter. So, for the block failure, previous one was single pile failure, now we are considering the block failure. So, my group capacity is the same as the single pile failure case. That means, this will be also CUNC into ABG, that is for group, plus again also we are taking alpha Cu, average cohesion along the shaft of the pile or along the pile group, ASG. Now, there is a question that in single pile the interaction is between pile and the soil. So, we are taking the adhesion factor, but now in the group pile, so it is a block. So, this block is basically interacting. So, but here the distance between the or the difference between the pile is more. So, that means here more soil will interact compared to the pile. So, that is why here the adhesion factor for group pile is considered as 1, because here basically the interaction between soil versus soil in case of group pile. So, that is why adhesion factor you are taking 1. So, that means here Cu is 35, again NC is equal to 9. Now, this is a square pile group whose B is 2.3. So, this will be 2.3 square, okay, plus adhesion factor is 1, Cu is 35, then the area or the perimeter is 2 into 2.3 plus 2.3 and length is 15. Perimeter into the length, that will be the surface area. So, that is equal to 6496.4. So, that is the load carrying capacity of the pile considering block failure. So, the minimum of these two we have to consider as the load carrying capacity of the pile block. So, this will be 3131.4 kilonewton. That is the group load carrying capacity. And remember that, suppose as I mentioned in my previous lecture, that the efficiency of the pile group is this pile load carrying capacity considering the block failure or the group, and then the number of pile into the load carrying capacity of the single pile. So, now if I consider this condition, then this is 31901, this is 6496. So, that means group efficiency is greater than 1. No, this is not the case. Group efficiency is 1 here. So, as I discussed in my previous class, the spacing is sufficiently large, then that block failure will not occur. Then the pile will failure as single pile failures. In that case, your efficiency will be 1. So, here this is the case. So, that means here the block failure is not occurring, it is the single pile failure is occurring. That is why that is the lowest value it is given compared to the single pile and the block pile failure. So, here efficiency will be 1. Okay. So, we cannot say this is the efficiency. When there will be a group pile failure, suppose your this block failure is given lower amount of load carrying capacity compared to the single pile failure. In that case, you can use this expression and put the value, you will get the efficiency less than 1. So, that will be the efficiency of your pile group. But when the single pile failure is giving lower value compared to the block failure, that means the spacing is sufficiently large, that is why we are getting a single pile failure. So, in that case efficiency will be always 1. Efficiency cannot be greater than 1 except one case that I have discussed for the loose sand driven pile. In that case also we will get the efficiency greater than 1, but that case also during the design you consider efficiency is equal to 1. So, that is why these minimum spacing recommendations are given. So, if we take more than 3D in case of pile, so in that means we will get efficiency close to 1. So, there will be a single pile failure. Okay. So, that is why here efficiency is always 1. So, in this case efficiency, pile group efficiency is 100%, because it is a single pile failure in okay. And then but group value is 3191.4. So, what is the factor of safety? Let us determine that. So, factor of safety will be your or QUG safe. Safe load will be how much? That QUG divided by factor of safety, and factor of safety we are taking 2.5 to 3. So, here we are taking 2.5. So, 3191.4 divided by 2.5. So, this is 1276.6 kilonewton. So, how much load is coming? The load is coming 1125 kilonewton, and the pile can carry safely, or the pile group can carry safely a load 1276.7. So, a design is safe for the bearing capacity consideration. So, this is greater than 1125 kilonewton. Okay. So, in terms of bearing capacity consideration, design is safe. What are the values we assume? Number of piles, spacing, diameter, length, that is absolutely fine for the bearing capacity consideration. Now, we will check it for settlement consideration. Okay. So, for the settlement consideration, so this is the pile group, and we are mentioned here in the question that the soil is in greater depth, the extension of the soil layer. So, that means here we consider it is a homogeneous soil. So, we will put it at the 2/3 from the base of the or from the top of the pile. So, here we will place the raft, and that means this is 2/3 L, this is 1/3 L. So, L is 15. So, 2/3 L is equal to 10 meter and 1/3 L is equal to 5 meter. Okay. And then our B value is 2.3 meter. So, influence zone will be twice B. For the settlement calculation will be 4.6 meter from the raft. So, that is within the pile group itself for this particular case. So, this will be 4.6. So, we will take a point for our settlement calculation A, which will be half of that 4.6, that means 2.3 from the base of the raft, because it is similar as the shallow foundation design or raft design. So, now the Qn which is coming at this level, I mean stress, net stress which is coming. So, load is 1125, dimension of the raft is 2.3 cross 2.3. So, this load is 212.7 kilonewton per meter square. Okay. So, we will calculate the immediate settlement, which is Qn B 1 minus mu square divided by Es and If. Okay. So, for the square foundation L by B equal to 1, that If at the for the flexible footing at the center is 1.12. So, this is for the center for flexible foundation. Okay. But here we have considered it is a raft. So, it will be a rigid foundation. So, now Qn is equal to 212.7, B is 2.3, mu is 0.5, this is 0.5 square. Mu value is given in the problem, no, it is not given. So, for the clay we are assuming that mu value is 0.5, 0.5, this is for clay. So, elastic modulus of the soil is given, elastic modulus of the soil, no, it is not given in the question, but I should write that thing also. The elastic modulus of the soil is missing, but it is given in the problem. So, elastic modulus of the soil is given 26 into 10 to the power 3 kilonewton per meter square. So, it is given. If it is not given during design purpose, I have given you a number of correlations based on CU also there are some correlations are given. So, in my previous raft design problem, I have used one of those correlations. So, you can use those correlations and you can determine the ES value, but in this particular problem it is given, but it is given. So, in this is given ES equal to 26 into 10 to the power 3 kilonewton per meter square. But here I am doing a design problem. So, that is why you can assume few things, but when you solve a problem in exam and or assignment, I will specifically I will give every data, I mean even mu value, everything I will give, because otherwise you will not get a particular answer. But here for design I can assume during the design, but actual when you do a assignment problem or exam problem, those data will be given. So, I can write that ES is given. So, this is mu square divided by ES, which is 26 into 10 to the power 3, then IF value is 1.12. Okay. So, that means the value is coming 15.8 millimeter. Then you have to apply the corrections. So, corrections we have to apply the rigidity correction. rigidity correction factor is 0.8 because we have taken the IF for flexible foundation at the center, and the depth correction factor for the immediate settlement, and for the consolidation settlement there will be a pore pressure correction also. This correction factor. So, what will be the depth correction factor? Now, here in my shallow foundation design, I consider the upper part of this chart, okay, that was d by root LB. So, this chart was given in the IS code. So, I used the same chart which is d root over LB for the shallow foundation design, but for the deep foundation design that upper part is not sufficient, you have to use the lower part. Okay. For shallow foundation is the upper part, lower part is for the deep foundation design, and L by root over LB by D. So, root over LB is 2.3 into 2.3 and D is here, the depth of foundation is 10 meter because that is the depth of foundation. So, we can write this is 0.23. So, for L by B is equal to 1 and this is L by B equal to 1 and it is 0.23. So, 0.23. So, 0.23, this is the value. So, this value will be around 0.56. Okay. So, this value is around 0.56. So, the correction factor is 0.56. So, the EI corrected is equal to 15.8 into 0.8 into 0.56. So, that value is 7.1 millimeter. So, that is the corrected immediate settlement. Now, we will calculate the consolidation settlement. Okay. So, consolidation settlement is CC 1 plus E 0 H, because here is a single layer. So, I will take the single layer values, and this is P 0 bar delta P divided by P 0 bar. So, at point P, at point 1 A, this is the point A, which is 2.3 meter from the base of the raft. So, P 0 will be, and water table is at the ground surface, water table is at the water table is considered at the ground surface. So, water table is here. So, all the unit weight we have to consider the submerged unit weight, and at point A, which is 10 plus 2.3, 12.3 meter from the ground surface. So, it will be 10 plus 2.3. So, this is 20 minus 10. So, 10 we are considering unit weight of water is 10 kilonewton per meter cube. So, 20 minus 10. So, this is 1, 2, 3, 12.3 into 10 kilonewton per meter square. And then we are considering 1:2 distribution, 1:2 distribution. Then this will be 212.7 into 2.3 into 2.3. Then this is 2.3 and the depth is also 2.3. Then 2.3 plus 2.3. So, this 1:2 distribution I have already discussed. So, then it will give you 53.2 kilonewton per meter square. So, the uncorrected consolidation settlement CC is 0.1, E 0 is 0.9, I think CC is 0.1, CC is 0.1, E 0 is 0.9, gamma side is 20, that is why we have taken 20 here. So, 1 plus E 0 is 0.9, thickness H is the thickness and H is 2B and 2B is 4.3, sorry 4.6. 4.6, this is 4.6 influence zone. Okay. So, So, 4.6 into log 10 123 plus 53.2 divided by 123. So, this is 37.8 millimeter. So, what are the corrections you have to apply? So, again the rigidity correction, factor which is 0.8, then depth correction factor which is 0.56 we have already determined, then pore water pressure correction factor which is given 0.7, which is given I think 0.7, yeah, 0.7, pore water pressure correction is 0.7. So, now if I calculate the corrected consolidation settlement, that will be 37.8 into 0.8 into 0.56 into 0.7. So, that will give 11.9 millimeter. So, the total settlement of the pile group will be equal to, the immediate settlement was 7.1. So, 7.1 plus 11.9 which is equal to 19 millimeter. So, it is less than 25 millimeter, which was the permissible settlement for this particular design. So, that means the design is safe in terms of bearing capacity as well as the settlement. So, this way we can determine the bearing capacity of the pile group and the settlement of the pile group. So, that I have done for the clay. Similar way, exactly by using that sand bearing pile bearing capacity equations, you can determine the bearing capacity of the pile group in sand also and the settlement of the pile group in sand also. Okay, because I have already discussed the settlement of the raft resting on sandy soil or settlement of the shallow foundation resting on sandy soil. So, same equations you can use, because I have used a similar type of equation here for settlement calculation of the pile group or the raft for clay. So, in the next class I will discuss the last topic of this pile foundation under compressive load, that is the negative skin friction. So, next class I will discuss the negative skin friction, then I will go for the next topic, that is lateral loaded pile. Thank you.